you guys can all breathe a big sigh of relief because we are done with stoichiometry officially. So any math that we do in this unit is going to be a lot simpler, a lot fewer steps to it, and we won't have to worry about stoichiometry for at least a couple weeks until we go back to something that needs it again later. All right, what we are talking about in this unit is gases. So we're going to talk about kind of the laws that govern the behavior of gases and what makes them different from other states of matter. So first of all, we talked about this a little bit back when we first went over states of matter, but there are two main things that determine what state a substance will be in. Okay, one of them is the forces that hold the particles together. So that can be charges in the case of an ionic compound, or gravity between particles, or any other intermolecular forces that are pulling those particles together. All right, the second thing, and probably the more important one, is the kinetic energy present in the substance. So anything that's a solid tends to have a much lower kinetic energy than a liquid or especially a gas. So kinetic energy tends to make the particles move and pull farther apart from each other. And it's very closely related to temperature. So in a gas, the particles are moving around a lot faster, which gives them a much higher kinetic energy. And that's why gases tend to occur at higher temperatures than the other states of matter. If we use water for an example, right, when you cool water down and freeze it, it has a very low kinetic energy. It's a solid. You heat it up a little, it melts. And then if you keep heating it and keep raising that kinetic energy, eventually it will boil and turn into a gas. All right, gases have some characteristics that make them different from any other state of matter. So one thing that they do is that they will expand to fill up any container that you put them in, right? They're not all clumped together like a solid or a gas. Those particles are moving so quickly that they're bounced around all over the place, and they just go as far apart as they can and fill up whatever container they're in. So because of that, because they're so spread far apart and there's so much empty space in between them, gases have very low densities, right? They take up a lot of volume for not very much mass. And that means that they can be compressed, unlike any other state of matter. So you can take those particles and squish them down closer to each other to fit more gas in a smaller space. So think about like a scuba tank that people wear to dive with. You can fit hundreds of breaths of air into a relatively much smaller volume by compressing those particles down together. And you can't do that with any other state of matter. All right, the next thing we've got to touch on is the concept of an ideal gas. So when we do the equations and the laws later in this unit, we're going to be assuming that the gases we're working with are ideal gases, because it makes the math a lot easier. Particles in an ideal gas, one thing is that they have no volume. Right? Now, obviously, that's not true, right? In a real gas, in the real world, the atoms in the gas itself, they take up space. They have volume. But because they're so spread out and so far apart from each other usually, we can make the assumption that they have no volume and it doesn't affect things too much. Okay, the second thing that we're going to assume is that the particles in an ideal gas have perfectly elastic collisions. So if you guys haven't taken physics before, then you have no idea what an elastic collision is. But basically all it means is that when the two particles hit each other, they don't lose any of their kinetic energy. They bounce off and they go back in different directions, but neither of them slows down. So think about like pool balls. If two of them are coming together and they hit each other and bounce right back off and go opposite directions, no kinetic energy was lost there. The other thing that we assume about them is that they are in constant random straight line motion. So they are not taking any wavy, curvy paths or anything like that. They move in a straight line until they hit either another particle or the wall of their container, and then they bounce off that and move in another straight line, and they keep repeating that all around, bouncing back and forth around their container forever. And because they don't lose any kinetic energy when they make these collisions with each other, they never stop. Okay, we're going to assume that they don't attract or repel each other, so that there's no charges between the protons and the electrons or anything like that that messes it up and adds resistance to these collisions. And then the last assumption is that they're going to have an average kinetic energy that is directly related to the temperature. So as your temperature goes up, they move faster and your kinetic energy increases. So those are the assumptions that we're going to make for an ideal gas. The problem with that is that they're all false, right? In a real gas, in the real world, the particles do have volume, and they do have intermolecular forces that attract each other. So that means that when they hit each other, those collisions aren't going to be perfectly elastic. So energy is going to be lost in each collision. That's one reason why things tend to cool down over time. Like if you heat up a bunch of gas and just leave it, as those collisions happen, they lose some of that kinetic energy every time, and so the temperature goes down, 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 down. But we can get the closest to the ideal gas behaviors at relatively low temperatures and relatively high pressures. Sorry, I said that totally backwards. We're closest to the ideal gas behavior at low pressures and high temperatures. So the reason that is that at STP, which we'll talk about in a minute, but it stands for standard temperature and pressure, the molecules of a gas are moving very fast and they're very far apart, which means that their intermolecular forces and their volumes to each other, they don't really matter. They're insignificant. So we can assume that they behave like an ideal gas, and we will be, for the most part, correct. But if we have a very high pressure, that means all those gas molecules are squished closer together, and they have more and more interactions with each other. So that's going to throw things off, because if the interactions are happening more often, then they're losing more kinetic energy. I don't know why I said it like that. They're losing more kinetic energy at a faster rate because these reactions are occurring quicker. All right, at very low temperatures, the gas molecules move very, very slow. And so when they do collide with each other, those intermolecular forces might be enough to keep them from bouncing back apart. So high pressures and low temperatures means that the ideal gas assumption kind of falls apart. But for the vast majority of problems that we work with, where we're working at temperatures and pressures close to what we actually experience on Earth, ideal gases are good enough. Okay, so there are two big kind of forces and characteristics that affect how a gas behaves. All right, and the first one we're going to talk about is pressure. So the general definition of pressure is force divided by area. So if you guys have heard the unit of pressure of PSI, that's pounds per square inch. So like if you look on the wall of your car's tires, it'll tell you this tire is rated for 60 PSI. That means that every square inch of that wall of the tire is holding back 60 pounds of pressure from the air inside of it. So if we look at these shoes down here, assume that the same person is wearing all three, so the force is going to be equal. Which shoe is going to create the most pressure on the ground beneath it? So if the force is equal, that means the pressure has to be related to a change in area somehow. So if we look at the area on the bottom of these high heels, a lot of that pressure is going to be concentrated, a lot of that force is going to be concentrated on this very small point, right? So it has a very small area. That means we're going to have a high pressure on that point. So tennis shoes here, they're, a nice big flat area on the bottom. So you've got definitely less pressure than the high heels. and the snowshoes are the other extreme. They spread that force out over a big wide area so that there's much less pressure. So that's why snowshoes work, right? You can stand on top of the snow and have that pressure spread out enough that you don't break through it and go all the way down. And trying to walk in the snow in high heels would be a disaster. So they take advantage of this to create less pressure so you can walk on top of the snow. What does that have to do with gases? Well, the force of a gas on its surroundings has to do with how many collisions it's making with the outside of its container, per second or per amount of area. So if you've got balloons with different pressures in them, the one that has more pressure just means that it has more collisions occurring with the outside of that balloon. Okay, there's also the concept of atmospheric pressure, which is the pressure that we feel just by being outside and having the air kind of pushing down on us or pushing in on us. So because Earth has gravity, it pulls most of the molecules in the air down towards it. So pressure is going to be higher at sea level because there are more of these molecules hitting you every second. And then as you go up and up and up into the atmosphere, there is fewer molecules of air, and so there is less pressure. So when you get in an airplane and you go from sea level up into the upper atmosphere where there's a much lower pressure, your ears have to kind of pop and let the air that's inside of them out to accommodate for that, because that change in pressure messes with the air inside your eardrums. So the way that they used to measure this atmospheric pressure is actually, it's kind of ingenious. What they did is they had a little pool of mercury, and they took a test tube and they sucked all the air out of it. So there was absolutely no air inside that test tube. It was a total vacuum. And they put it upside down into the mercury. And so what happened was the pressure from the atmosphere would push down on this puddle of mercury. And as it pushed down, it forced the mercury up into that empty test tube. So what they would do to measure pressure with this is that they would just measure how high the mercury got. So if you took this down to the ocean and you held it there and you measured how high it got, it would have a temperature or a pressure of a given, height of the mercury, and then you took it up in an airplane up into the upper atmosphere. Well, there'd be less pressure pushing down on the mercury, so it wouldn't go up as high into the tube. So it would be a lower pressure. So that's why one of these units that we use for pressure is called millimeters Hg, or millimeter mercury, because that's actually how they used to measure it. Okay. The other units that we use for pressure are kilopascals, atmospheres, torr, and the one that you guys might be the most common with is PSI, pounds per square inch. So all of these units that you see here are equivalent to each other at standard atmospheric pressure, which basically just means the pressure at sea level on average. So 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.325 kilopascals, which is equal to 760 torr. Honestly, I don't know why torr is its own unit. It's the same thing as millimeters of mercury, but someone decided to use it. So I wouldn't worry too much about it. And then PSI is pounds per square inch. So what that means is at sea level, our bodies feel 14.7 pounds of pressure pushing on them of every square inch of your skin, which is kind of crazy when you think about it. But we don't ever notice it because that's just how we've adapted, how life has evolved on the surface. If you go down into the deep sea where there's a lot of water pressure pushing down on things, those animals down there feel tons and tons and tons hundreds of psi of pressure pushing on them, and they've evolved to life down there. But when you bring them up and the pressure decreases, it causes all kinds of problems. Same thing as if you took a human, put them up in space where there's no pressure. We're just not designed to survive that way. So it's kind of interesting to think about. Okay, there's such a thing as STP, which is standard temperature and pressure. And what that is 0 degrees Celsius at 1 atmosphere. So the freezing point of water at sea level is standard temperature and pressure in chemistry. And then that's equivalent to 270 degrees Kelvin and 101.325 kilopascals. Okay, the other thing, other than pressure, that affects gases is temperature. All right, and when we are working with gases, we're going to use what's called the Kelvin scale of temperature. And basically what it is it's the same as Celsius, but you are just adding 273 degrees to whatever the Celsius measurement is. And you're like, that seems super random. Why would we do that? Well, because negative 273 degrees Celsius, or 0 degrees Kelvin, is what's considered absolute zero. So what that means is, for any substance, no matter what, the molecules in it are always moving around, right? They're always vibrating and jumping around, and in gases, they're bouncing off the walls and everything. But at 0 degrees Kelvin, the motion stops completely for everything, right? So, the reason we use this as our scale is because you can't get any colder, any less kinetic energy than 0 Kelvin, which means in Kelvin, there's no such thing as a negative value for temperature. So it just makes things a lot easier to use that because we don't have to worry about having, negative degrees that we have to keep track of and throw our calculations off. All right, so here's some examples of converting between Celsius and Kelvin. Remember, if you're going from Celsius to Kelvin, you're going to add 273. And if you're going from Kelvin to Celsius, you're going to subtract 273. So here, 0 Kelvin plus 0 Celsius plus 273 is just going to be 273 degrees Kelvin. And technically, you don't actually say degrees Kelvin. You just say 273 Kelvin. You don't have to draw the little dot. But I'm not going to count off points if you do. All right, same deal here. If you have 100 degrees Celsius, you add 273 to get to Kelvin. So this would be 373 Kelvin. Okay, our next one here is room temperature, 25 degrees Celsius. You're going to add 273. It's going to come out as 298 Kelvin. And then this one, the reason that we use Kelvin, the reason that it's useful, is because Celsius can very easily get into the negatives. And negative numbers are a pain in the butt. So if we convert this to Kelvin, it's always going to be a positive number. So if we have negative 12 plus 273, that should come out as 261. And bear with me here, I'm drawing all this with a mouse, so my handwriting's not going to be great. Okay, this one here, kind of a trick question. It's asking you, what would negative 273 degrees Kelvin be in Celsius? But the whole point of Kelvin is that there's no such thing as a negative number. So this just doesn't even make sense, right? Not applicable. These ones, on the other hand, you can do. If we're trying to go from Kelvin to Celsius, we're going to subtract 273. So 23.5 minus 273. I don't want to do that in my head, so comes out as negative 249.5 degrees Celsius. And then the very last one, 373.2 minus 273 gives you 100.2 degrees Celsius. Alright, so these conversions aren't too bad. Just make sure you kind of check yourself as you go. And if you get one like this where your answer, like if we had just done this without thinking about it, we would have come up with negative 546 degrees Celsius, which is like twice as cold as anything can possibly be. So just make sure you're checking yourself that you don't ever have a negative value for Kelvin. All right, let's move on. So now that we've kind of talked about the forces and characteristics of gas, we're going to start talking about laws that we can use to describe how they behave. All right, the first one is what's called Boyle's law, and it has to do with the relationship between volume and pressure in a gas. So let's say we've got a syringe like it's shown there, and if you plug the front of it with your thumb and you push on the syringe, what's going to happen, right? As you push that plunger down, the volume inside there is decreasing, right? It's going from, on the top of this, it's got 12 cubic centimeters, and as you push that plunger down, it's squishing all the gas in there into a smaller and smaller space. So down here, it's only in 3 cubic centimeters. So as you push that further down, does it get easier to push the plunger or harder? And do you feel any pressure pushing on your thumb? Does that pressure increase or decrease as the volume goes down? If you've ever done that before with anything, or used like a plunger, right? As you push it down, it gets harder to push it because the volume in there is decreasing and the pressure is going up. You'll know that that's kind of the basis behind Boyle's law. So you can see here in this little example, when there's more room, those molecules are bouncing around and there's more space in between them. So they're exerting less force on the walls of their container. So there's less pressure. If the volume decreases, those particles that are bouncing around, well, they now have more collisions per second or per area with the side of their container. So they're exerting more force and the pressure is going to go up. All right, this is a picture of the guy who came up with this idea. But basically what he said is that the pressure and volume of a gas are inversely proportional. So as one increases, the other decreases, and vice versa. And this only works if the mass and the temperature are staying the same. So when we're talking about Boyle's law, we don't care what temperature it's at, as long as it doesn't change throughout the reaction or throughout the process. All right, and so a graph of that would look something like this. As your pressure goes up, it means you have a lower and lower volume. And as your volume goes up, your pressure is going to decrease. And the way we can write that as a formula is that P1V1, so this is the pressure of the gas initially and the volume of the gas initially, so what they start as, and we're going to say that's equal to the final pressure times the final volume. All right, so when you get problems for Boyle's law, you're going to plug things in and solve it for whichever one of these 4 values the problem doesn't give you. All right, so if we're looking here at an example problem, let me bring my little marker back up. Sorry, let me just get rid of all this real quick. What? Why would it come back? Ah, there we go. Okay. Okay, so if we look at this problem, it tells us that we have a weather balloon with a volume of 2,000 liters at a pressure of 96.3 kPa. So it rises to an altitude of 1,000 meters where the atmospheric pressure is measured to be 60.8 kPa. So assume there's no change in the temperature or the amount of gas, and it wants to know what the final volume of that balloon will be. So just real quick sanity check. If it originally started off as 2,000 liters at this pressure, and then the pressure decreased to this, do we think that our volume should be bigger or lower as the balloon goes up? So if we look back at our little graph on this previous slide, we're saying that our pressure is going down, which as our pressure goes down, it means our volume should increase. So if we do this math and we come up with something that doesn't match that, we know we probably messed something up somewhere. All right, so let's write out our equation here. P1 times V1 is equal to P2 times V2. And then we're going to start plugging values in. So our pressure 1 is 96.3 kPas. And the good thing about this equation that we're using here is that because it's totally proportional, we don't care what unit this is in, as long as they're both the same unit. It can be kPas, it can be atmospheres, it can be millimeters of mercury. It doesn't matter as long as we use the same one on either side of the equation. So we plugged in P1, and we're going to plug in V1. So we've got 96.3 times 2,000. We're going to say that is equal to P2, which is our 60.8 kPas times V2. All right, and then in order to solve this, all we've got to do, multiply these two together. That's 96.3 times 2,000 gives us 196. Nope. 192,600. Alright, and then get V2 by itself by dividing both sides by the 60.8. So we're going to take our 192,600 divided by 60.8. And it comes out that V2 is equal to 3167 0.76 liters. All right, and then like we said, our sanity check, was that our volume should increase from the original, and we did, right? We started at 2,000, the pressure went down, now our volume is 3167. Okay. Let's do one more example on this. Ooh. So here, we've got another one. Tells us the atmospheric pressure on the peak of Kilimanjaro can be as low as 0.2 atmospheres. So it tells us the volume of an oxygen tank is 10 liters. At what pressure must the tank be filled so that the gas inside would occupy a volume of 1,200 liters at our 0.2 atmospheres? So we want to know what pressure our oxygen tank has to be so that it can hold 1,200 liters at 0.2 atmospheres. So we've got our equation again. P1V1 is equal to P2V2. And we're going to start plugging things in. So we know that we have 0.2 atmospheres of pressure times our volume, which is 1,200 liters. And we're going to set that equal to our P2 times 10 liters. Okay, and if we're thinking about this, our volume is going way down, right? From 1,200 liters to 10 liters. So as volume goes down, that means our pressure should increase. They do the opposite of each other, right? It's an inverse relationship. So our answer for P2 should be much, much higher than 0.2 if we set this up correctly. So let's do the same thing we did last time. 0.2 times 1,200 comes out as 240. And then to get P2 by itself, we divide both sides by 10. And it comes out as 24 atmospheres is our P2. Right, so much easier math than the stoichiometry, right? You're basically just plugging stuff into this formula and solving for one of the variables. The only tricky part is reading through the problem and understanding which one needs to go where. Okay, so you guys have 2 assignments to work on today. One of them is about converting between Celsius and Kelvin, and one of them is using Boyle's law to determine relationships between pressure and volume. We're going to talk about the rest of the slides in this PowerPoint about Charles' law and Gay-Lussac's law and all them tomorrow. So today, work on those 2 assignments, get caught up on any other assignments you haven't done for the past stoichiometry stuff, and please make sure you've taken your stoichiometry test. That way you don't have a big old fat 0 on it on your report card.